Today, in section 1.2, we'll talk about a particularly important kind of geometrical object built out of ones we've already encountered. I mean angles. This I don't think is particularly difficult. It's certainly shorter than the previous section that we did, but well, we have to be very careful about how it is that we name the objects that are involved. We'll move slowly through this. All right, so first of all, of course, I owe you a definition. An angle is a pair of rays with a common endpoint. That's it. Okay, an angle is two rays, and if they share their endpoint in common, then indeed it does make an angle. Those two rays are called the sides of the angle, and their common endpoint is the vertex. Okay, so that common endpoint is, of course, a point, so the vertex of an angle is a point. So look at our diagram. We have a pair of rays, one called GF, the other called GH. They do have a common endpoint, which is the point G. So together, those two rays make an angle, and its vertex is that common endpoint G. Now, as for angle names, this is somewhat complex. We'll find that actually we have three possibilities here, one of which always works, the other two only sometimes. Now, the first way, the way that always works, is to give an angle a three-letter, capital letter name based upon points, of course. So the angle name would then have this particular form, and I'll circle this for you. First of all, angle symbol, that's what comes first in the circled portion. And then we have three blanks to fill in, and into those three blanks go capital letters. And the requirement about those capital letters is this, is that first of all, the middle one is the vertex. The first one is a point on one side, and then the final point name is a point on the other side. So look at the example that I gave you, where we have two rays with a common endpoint, the two rays GF and GH with common endpoint G. So of course, then we have an angle by definition. So one way to name this angle would be angle symbol, again, FGH. And notice that the vertex name G does come in the middle. And then F, which comes first, is a point on one side. And then H, which comes last, is a point on the other side. And a perfectly acceptable name as well would be angle HGF. And the reason that it's acceptable is because, again, the middle letter is G. And then to the left of G, we have a point on one side, and on the other, we have a point on the other side. So, of course, you draw the obvious conclusion that we can always exchange the first and third letters to get another valid name of the angle. Now, of course, we could also create invalid names for the angle that's present in the diagram. We could attempt to call it angle GFH. That's incorrect, because if it were GFH, the vertex would be F, but it is not. We might try to call it FHG. And again, since the vertex is not H, that cannot be correct. Now, sometimes, in some situations, and I almost hesitate to tell you this because some of you will abuse it, in some situations you can name an angle with a single letter, that is, with the vertex letter. So, for instance, in the diagram below, you could call the angle that's present simply angle G. Now, you might wonder to yourself, well, that seems so much simpler, and I suppose it is, than the name that involves or makes use of three letters, so why not simply always do that? Well, the answer is that you can't always do that, because like in the diagram that you see, sometimes you have more than one angle with a particular vertex. So, well, here's a good question for you. How many angles do we have in this diagram with vertex G? You might have thought two. And when you said two, no doubt you had in mind the two angles that I'm about to indicate by use of the arrows. But a third angle was also present as well. So, of course, we did have three angles. Now, the reason, and this is my point here, not the number of angles, but angle names, my point is that you couldn't simply call any of these angles angle G, because you wouldn't know which angle is meant. Do you mean the one on the top? Do you mean the one on the bottom? Do you mean the whole composed of those two parts? So the requirement always, of course, is that when we name an object, we name it unambiguously, so we know clearly to which object that name refers. But if we were to call in the diagram an angle simply angle G, we wouldn't know which of the three is meant. So in a situation like that, we shouldn't use a single vertex name. If we wanted to name one of the angles that was present in the diagram, we could pick some points on sides. So I don't know, how about point X and a point Y? And if we wanted to name the angle on top, we could then call that, for instance, angle XGY. y. And then we would have unambiguously named one of the angles that was present in the diagram. Now, we'll often use number names for angles as well, the positive integers 1, 2, 3, 4, and so on. And we do this because it's extremely convenient. And very often what we'll do is we will tuck the number into the interior of the angle next to its vertex. So clearly, then in such a case, the number will name a particular angle that is present, like in the diagram that you see. The number 1 angle also labels angle RZS, and angle 2 also labels angle SCT. This is a very common way and a very convenient way to name angles, to place that positive integer into the vertex. And notice, of course, that there's no temptation here to confuse this as a measure, because it doesn't have that usual measure symbol for angles on it, the degree symbol. We will come and talk about degree measure later on, but I'm sure there'll be no confusion here. Straight angle. A straight angle is an angle whose two sides form a line. Note that we do not say in this definition what straight angles measure, okay? I do not mean to say to you that I have no opinion about what straight angles measure. I do have an opinion about that, and I will express that opinion to you in the next section. However, I do mean to say to you that the definition doesn't say anything about what that measure is, because it need not, okay? The point of a definition is to teach us how to use a term. It is not to say everything that is true about that term. So if I say that a straight angle is one whose two sides form a line, then I have taught you how to use that, and that's all that I will say. So look in the diagram. So if we know that rays AB, that is the one that starts at A and passes through B, and the ray AC, the one that starts at A and passes through C, if they do indeed form a line, then the angle BAC is straight. And notice that we couldn't call this, for instance, like angle CBA, because if we said CBA, B would be the vertex because it was in the middle. In this case, our straight angle has vertex A, so we could call it angle BAC, or equivalently angle CAB, both with A in the middle. Adjacent angles, an extremely important concept for us. We say that two angles are adjacent if they have a common side. That is, if a side of one is identical to a side of the other, and their interiors do not overlap. So look at our diagram. So consider angle BAC, the one that's composed of ray AB and ray AC, and then consider angle DAC, the one that's composed of rays AD and AC. They do have a common side, okay? How about I make that bold for us? The common side is the ray AC, but their interiors do not overlap. The interior of BAC lies above AC. The interior of DAC lies below AC, so their interiors do not overlap, so we say that they are adjacent. So adjacent angles. Vertical angles, an extremely important concept as well. We will prove theorems in chapter 3 about adjacent angles of a particular type, and we will also prove a theorem about vertical angles. For now, we simply define them, but we will find that these are extremely important ideas. We say that two angles are vertical when their sides form two lines. Okay, now look at the diagram, and let me make sure that you understand what's been said here. So look, for instance, at angle AVC. I just picked it out, and angle DVB. Well, to get those two angles, of course, we have four rays, right? We have the ray VA, VC, VD, and VB. And notice that those rays, which are the sides of the two angles, form two lines. So together, VA and VB make line AVB, and VC and VD make line CVD. So these two angles, okay, their sides form two lines, and that means that they are vertical angles. Here's another equivalent definition of vertical angles, and either is perfectly acceptable. Two angles are vertical if they're an opposite pair formed when two lines intersect. And maybe you'll find that one clear. So look back at the diagram. I've got the two lines, the one that goes from A to B to B, and then the second line that goes from C to V to D. And obviously those two lines intersect at B. And then pick a pair of angles that lie opposite one another, okay, like the AVC and the DVB. Those are a vertical pair. Now, of course, there will be another vertical pair as well. Like, for instance, if one were to take AVD and CVB, okay, notice that those are also a pair of angles that lie opposite one another when two lines intersect. So the general point then is this, is that whenever we intersect two lines, we get two pairs of vertical angles. Linear pair, we say that two angles are a linear pair when they're adjacent and their non-common sides form a line. Okay, so let's think about what precisely that means. Okay, so first of all, we say that they're adjacent. That means that they have a common side. So look at the two angles in my diagram, the angle MOP and the angle NOP. They do have the common side OP, okay, and their interiors do not overlap, okay, so they're adjacent with common side OP. And then look at their non-common sides. And I tell you what, I'll get a different color for this. How about green? So look at their non-common sides. That is the sides that are not in the intersection, the sides that are not in common. That's ON from one, OM from the other. And notice that those non-common sides form a line. So there you go. That's a linear pair. And it should be fairly clear why this is called a linear pair, right? Because we do have two angles, and together they make a line. Now, here's a good question for you. This is actually something that is sort of the foundation, the insight behind one of the proofs that we will do in chapter 3. So look at the diagram. No doubt you will recognize this as the diagram that we used for vertical angles, and we've got two pairs of vertical angles. So how about we use numbers? So 1 and 2 form a vertical pair, and 3 and 4 also form a vertical pair. Now here's a question for you. Do we have any linear pairs? Tell you what, I'll list this out. So vertical pairs. Okay, so 1 and 2 is one, and 3 and 4 is the other. And do we have any linear pairs? Well, do we have any pairs of adjacent angles whose non-common sides form a line? Well, yeah, we absolutely do. And we have a lot, don't we? So for instance, look at 1 and 3. They have a common side, don't they? Don't they? That's line VA. And their non-common sides, that is VC and VD, they form a line, so that's a linear pair. Notice as well that 3 and 2 form a linear pair. Notice as well that 2 and 4 form a linear pair. And notice as well that 1 and 4 form a linear pair. So we actually have 4 linear pairs wherever we have 2 vertical pairs. But isn't that curious? And that actually will be quite important to us.